Last week, we were talking about the Liénard-Wiechert vector potential, and there we started with the current density associated to moving point charge, and we introduced the new type of green function and using Kronecker delta function. We were able to derive an expression for vector potential, which is called Liénard-Wiechert vector potential. And today we will talk about Liénard-Wiechert scalar potential, and then we will use this scalar potential as well as vector potential to derive the expression for your electric field, and then we will talk about magnetic field. But today, since the electric field is given by vector E is equal to minus del phi minus dou A by dou T, where your phi is scalar potential and A is your vector potential. So we will obtain the expression for those quantities minus del phi and dou A by 2 minus dou A by 2t, and we will plug into the relation that E equals to minus del phi minus dou A by 2t. So first we will complete this one, the Liénard-Wiechert potential, second part of this. This is the scalar one. So let us consider a moving point charge Q. The charge density associated to the moving point charge is given by this equation 12, that is rho equal to Q times delta function of this. And the Liénard-Wiechert scalar potential is given by this relation, as in case of your vector potential, that was vector A is equal to similar integration and this green function, and there was minus mu naught times J and dq r prime dt prime, as well as there was a factor which was r naught vector r naught dot, that was velocity term. But here in case of scalar potential, we don't have any factor, any factor like velocity. So here rho is your charge density, which is given by equation 12, and as we know, we are familiar with this GC cot, and the GC cot, this cost green function, can be expressed in terms of your Coulomb's green function, and Coulomb's green function is actually, it is minus 1 by 4 pi times some modulus of something, and we will plug that, and finally we will integrate twice, first with respect to r prime and then with respect to dt prime, t prime. So here in among these, between these two integral sign, first one is for r prime, which is integrated for all possible values of r prime, and similarly the other integration is sign of integration is for the variable t prime. So here, where the first integral is extended over this, and this cost green function is given by that, you are familiar with this. So you should keep this in your head, so that if you will be asked in final examination, you can write this and you can solve the problem. Okay, so here and this is given by this Coulomb green function, which has relation with this cost green function, is given by this relation, and GC is your Coulomb green function, that is, you are familiar with that, and it is given by minus 1 by 4 pi and factor modulus of this r prime minus r naught, which is function of t prime. And if you plug these into this GC cot, you will get this expression here, and probably anything is missing there. Delta is here. Okay, that's fine. Now we will plug this GC cot back into above equation, which is the initial expression for your scalar potential. So there we have this minus sign with 1 over this bonds. This is your Coulomb's green function, and this theta term and this delta function big one is all these connected with your this special green function, and this minus rho by epsilon that comes from the relation between your charge density associated to your moving point charge and scalar potential. And here dq r prime and dt prime, those are the variables that we are integrating here. So little bit simplify that, minus rho by epsilon naught, that epsilon naught can be taken here outside the sign of integration. Also minus 1 by 4 pi was there associated to Coulomb's green function, that also taken outside, and minus plus, so there will be no minus sign there. And we have this factor and other factor, those associated to your Gauss green function, and rho is there. Now next job is to plot the value of rho from equation 12. So rho is this one, q times delta function r prime minus r naught this. So now next job is to integrate with respect to r prime. So as we did in last week for vector potential. So when we do that, we will get rid of a couple of things here. These things. So I again repeat that I skipped some steps to eliminate this, but and also we will get rid of this delta function. This thing is survive when r prime equals to r naught, and also we will get rid of this dq r prime here, and one of the sign of integration when we integrate that with respect to r prime, and that whatever the leftover things will be phi equal scalar potential is equal to q over 4 pi epsilon naught. This q comes from your charge density, and we are left with delta function with these big ones over r mod of r prime minus r naught, which is function of t prime, and dt. And as we know that this argument of your delta function can be taken as your pi f, some function f of t prime. So you can write this way. This whole bunch is argument of this is f of t prime, and you can write this equation 14 just to replace this delta function whole this bunch. Instead of that, you write delta function of this functional f of t prime. So this is here from equation 15, and now this delta function of f function of t prime, that is delta function of functional, can be given in this relation that we have already done in previous derivation for vector potential, and it is delta t prime minus t naught over mod of f prime of t prime at t prime equals to t naught, because everything is calculated here in the retarded time. And again, I will repeat that retarded time means the time at the source, that in other words, when a point charge is moving, at some point it begins to radiate, it begins to emit the radiation. That beginning of emission of radiation, that time is called your retarded time, and that is denoted by t naught. So here f prime, this prime stands for dou by dou t prime of f. So f prime means dou by dou t prime of f of t prime. So as we did in last week, what we do is when we plug that into equation 14, you will get something, and after that, one of the job that we are supposed to do is we need to evaluate this mode of f prime of t prime in after a couple of steps. So okay, here we have this. Now you can integrate this with respect to t prime, and when you integrate that, you will get rid of this delta function things and dt prime things, as well as sign of integration. So you will left with this thing here, phi equals to q by 4 pi epsilon naught 1 by f mod of f prime t naught, and times this factor, and you know, everything is evaluated at t prime equals to t naught, which is called retarded time. Okay, so here this r prime minus r naught at t prime t naught of t prime, because this is evaluated at t prime equals to t naught. So that's why this thing is nothing but, it doesn't matter whether you write it t prime or t naught here, because it is evaluated at t naught when we plug t prime equals to t naught. So this is r, which is the magnitude of r prime, vector r prime minus r naught at t prime or t naught. Okay, so you can replace this whole bunch by 1 by r. So this is the expression here. We have phi, that is Liénard Wiechert scalar potential, is given by q by 4 pi epsilon naught and 1 by r times this mode of this f prime of t naught. Okay, next job is to evaluate this mode of f prime t naught as we did last week. Similar to that, just we are repeating the steps here. So, but you know what, in final examination, if someone asks you to derive your scalar as well as vector potential, then you don't have to evaluate this again and again. Just one is okay. Just in, for instance, if you first you obtain the expression for scalar vector potential, then you can directly plug the value of this mode of f prime of t naught equals to this mode, as you have already done in your vector potential. But if you will be asked either one of these two potentials, that means either vector potential or your scalar potential, then you must have to evaluate this in detail. So, okay, so f of t prime is, this is here, and f of t prime is equals to dou by dou f of t, and this is the same thing we have already done in last week. So here, these are the same steps that I'm going to repeat this. So we are finding this mode of f prime of t prime, that is nothing but it is mode of f prime of t prime evaluated at t prime equals to t naught. So this comes out to be mode of mode evaluated at t prime equals to t naught, and this is dou by dou t prime, and this whole bunch is your f of t naught t prime. So again we are doing the same steps here. So this is 0 when we operate that dou by dou t prime, and here so this one in first one is 0, and the second one is your dou by dou t prime of t prime is 1, and the third one is 1 by c dou by dou t prime of this whole bunch is r, as we defined already. So this dou r by dou t prime, that r is not vector, this is the magnitude of vector r. So as we did last week, again this -1 and this dou by dou r, dou by dou t prime of scalar r means dou by dou t prime of vector r dot vector r raised to the power 1/2. Okay, so you know that this means 1 by c is there, and when you operate that, you will have a 1 by 2 and 1 by 2 times 1 over square root of vector r dot vector r, and 1 by square root of vector r dot vector r means 1 by square root of r square. That means 1 by r. So one of the factor that in the first step of this derivation, differentiation. So that would be 1 by 2 times 1 by r. And next is to take the differentiation of this argument, that is dou by dou t prime of r dot r, and that is vector r square or scalar r square, that doesn't matter. So that will give you dou by dou t prime of this vector r square, that will be 2 vector r dot dou vector r by dou t prime, as we have here. So it is -1, it is 1 by 2. Did I mention? Oh, okay. So this is the same thing as that. So next step is to get this -1, and that I was talking about this 1 by 2, and this c is right there, and this one, when you differentiate this one, that will be your 2r dot dou r by dou t prime, and one of the factor is 1 by this capital R square, and this is nothing but 1 by r. So from equation 18, you can cancel 2 and 2 there, and this you will have 1 by cr there, and in above in the numerator capital R dot vector r dot dou r by dou t prime. Okay, and everything is evaluated here. T prime equals to t naught, and you know that dou r by dou t prime, that we have already proved last week, that is nothing but -b, because dou r by dou t prime equals to dou by dou t prime, and because this is the function of t prime and only t prime, that's why dou by dou t prime of this will be 0, and we will left with minus dou r naught by dou t prime of t prime, and that is nothing but -b. So if you plug that back into here, you will have minus minus plus, this term will be plus, and you will have 1 by cr times vector r dot vector b. Okay, let's see that. Okay, if you plug that back into here, you will have this one, this minus plus will be there. So finally, this mode of f prime of t naught is nothing but it is mode of f prime of t prime it evaluated at t prime equals to t naught is equal to -1 plus r dot b over cr, and it is evaluated at t naught, t prime equals to t naught. And the next step can be like if you divide this b by c, that will be vector beta. Okay, so you can do that also, as we have done in previous week, last week. So this, because this is the mode, so you can write -1 plus these bonds as 1 minus these bonds, so that doesn't matter because it is the mode and everything is evaluated there. And this is the thing that I said we divide just by we take the c to divide here, and that is b by c is nothing but your beta. So you have this one here. These are the things that I was talking about, and you can rewrite this thing as you can change the position of the sign there. So that will be equal to mode of 1 minus r dot beta r. You can take the LCM, and you can have vector scalar r minus rb whole over r. Okay, if you plug that back into equation 8, which is the expression for your scalar potential, Liénard-Wiechert scalar potential. That is nothing but it is the scalar potential of moving point charge. So that was actually phi equals to q by 4 pi epsilon naught times 1 over mode of f prime of t prime evaluated at t prime equals to t naught. So that is this whole bunch including this r. So you can take the LCM here, r minus vector r dot beta over r, and this r can be cancelled. So basically you have this expression here. So phi equals to q by 4 pi epsilon naught times mode of 1 by r minus r dot beta evaluated at t prime equals to t naught. So simply you can write in the general form, and it is obvious that everything will be evaluated at retarded time. So that's why we always do not stick with this condition. So it is obvious. So finally, we have the scalar potential for a moving point charge as phi equal to q over 4 pi epsilon naught times 1 by r minus r dot beta. Here, this is your scalar potential, or you can say Liénard-Wiechert scalar potential. So this is the one of the part that associated with Liénard-Wiechert potential for a moving point charge. Okay, so the next job is to find your electric field due to an accelerating point charge. So that means, so here we start with your very fundamental expression of some equation, Maxwell's equations, and after that we will derive that E equals to minus del phi minus dou A by dou T, and if we evaluate minus del phi as well as minus dou A by dou T one by one, and we plug back into that equation, and finally we will get an expression for electric field due to an due to a moving point charge. And especially there will be two separate part of that electric field. One is acceleration dependent part and other is acceleration independent part. That means only velocity dependent part. So we just ignore the velocity dependent part and we stick with the electric field, which is acceleration dependent part, because accelerating point charge can radiate the radiation. That means it can emit the radiation, and our main purpose of this chapter is to study the radiation due to a moving point charge, and that means radiation due to an accelerating point charge. So here we start with this Maxwell's equations, which is called okay, with this equation, what is the name of this equation? Anybody? Del cross E plus dou B by dou T equals to 0. What's the name of this equation?
Maxwell equation, sir. Third Maxwell equation.
Third Maxwell equation, and it has specific name. You know, right? This is called
Faraday's laws of electromagnetic induction.
Faraday's law, sir.
Faraday's, okay, yeah. Faraday's law of electromagnetic induction in the differential form, right? Okay, so here del cross E plus dou B by dou T. So you can plug B equals to del cross A, and you can write E. You can write E, and you have E there, and del cross E plus dou by dou T of del cross A. And you can take the del outside, and there will be a del cross of something, and that something is actually E plus dou A by dou T. And because of your curl of, if some curl of something is 0, then you can obviously write that something can be some negative gradient of potential. So that's why we plug here B equals to del cross A, and we have this del cross E plus dou by dou T of this del cross A. Now that can be written, that can be taken as, you can take this dou A by dou T inside. That means this term can be, the second term can have this can be written as your del cross dou A by dou T, and if you take this del and cross outside, you would have E plus dou A by dou T, and as the curl of E plus dou A by dou T equals to 0, that means this whole bond E plus dou A by dou T can be written as negative gradient of potential, and that potential is nothing but the scalar potential of this moving point charge that we are talking about, and we have already derived the expression for that expression. I mean that scalar potential. So since curl of this equals to 0, so that can be this can be with taken as the negative gradient of potential, and that potential in our case is nothing but Liénard-Wiechert scalar potential. So this whole bond, this E plus dou A by dou T is equal to minus del phi. So this is the idea, and if you solve for E from this equation, you may have equation 2, that is vector E is equal to minus del phi plus dou A by dou T. Now next job is to evaluate dou A by dou T, and after that we will evaluate minus del phi, and we plug back these values of minus dou A by dou T and minus del phi into equation 2, and we separate the acceleration dependent and acceleration independent part of that electric field, and we stick with the acceleration dependent part, and acceleration dependent part of electric field will be the same, will have the same expressions that we have already written in some slide, maybe in the beginning of this semester, or maybe last week, I mean in the starting of this chapter actually. Okay, so next is to evaluate minus dou A by dou T, and anybody, do you have the expression of vector A in your head right now? This A is nothing but Liénard-Wiechert vector potential. Do you have that expression for A in your head, not in your notes and not in other?
Q by mu 4 pi, and it's B R minus beta R.
Mu not
beta R.
Q over 4 pi.
And
Yes.
B
Vector B
R
over
minus over scalar R minus vector beta the vector R.
Okay. Probably that's mode, right?
Yes, sir, mode.
Okay, so let's write that. So since the Liénard-Wiechert vector potential of a moving point charge is given by, this is A equal to mu naught Q by 4 pi B over the scalar R minus R dot B. Okay. So now we plug that A into this relation here. I mean, our purpose is to find minus dou A by dou T. So minus dou A by dou T equals to minus dou by dou T of this thing, this whole bunch. Okay, right here. So therefore, minus dou A by dou T is equal to minus dou by dou T of this bunch. This is nothing but your vector potential, which is called Liénard-Wiechert vector potential. So now from that, this mu naught Q by 4 pi can be taken outside of this, and you can operate inside. And here you may have minus dou A by dou T equal to minus mu naught Q by 4 pi. And if you operate that inside, you will have this expression, because you can take this is as a product of two functions. One is B and other is times 1 by R minus R dot beta. So here this factor is outside, and differentiation of first times the second plus first function times differentiation of the second, that is dou by dou T of 1 by this bunch. 1 by this bunch means your R minus R dot beta raised to the power minus 1. So you may write this way. Okay, so here this dou by dou t of v, because your acceleration is dou v by dou t naught, because we evaluate everything at the retarded time. That means at the time where the point charge begins to emit the radiation. So that's why this dou v by dou t naught, that will give you the acceleration of the charged particle. So this dou v by dou t, it doesn't give that one. So we evaluate this way. So it can be written as this dou v by dou t of v can be dou v by dou t can be written as dou t naught by dou t times dou v by dou t naught, and this is here. Okay, now in second term, it is v is there, and when you operate that, this will be minus 1, that will be plus 1, plus 2, minus 2, and this minus sign comes here. So this is minus sign, and v over r minus r dot beta raised to the power 2. That is because there was r minus beta dot r raised to the power minus 2 in the numerator. So that will be plus 2 in the denominator. And after that, you have to differentiate again this argument of these things. The quantity which have the power minus 1. So argument of that is r minus r dot beta. So dou by dou t of this. Again, here you can do the same thing, because we are interested to obtain everything in the retarded time. So that means 1 by dou by dou t can be written as dou t naught by dou t times dou by dou t naught. And especially we operate this for dou by dou t naught. So let's do that. Okay, so here see, okay, this is here as we have done already in previous slide, and this is nothing but this is acceleration a, vector a, which is the acceleration of moving point charge, and minus v over this is here. And as I said, this dou by dou t can be written as dou by dou t naught by dou t times dou by dou t. Something happened here. Okay, so so we operate with dou by dou t naught here. If you do that, as we have already done that way, so this is dou r by dou t naught minus, and when you operate this vector r dot minus vector r dot beta with respect to this t naught, so that will give you the two term. Minus sign is there, this r dot times dou beta by dou t naught minus beta times dou r by dou t naught. Okay, so again, you know that how to evaluate this one, dou r by dou t naught. Dou r by dou t naught can be evaluated as dou by dou t naught of vector r dot vector r raised to the power 1/2, and again we go differentiation as we have already done many times. Okay, so here minus dou by dou t. Okay, so minus q naught by mu naught q over 4 pi. That's the factor as we have. And this is here, there nothing change in first term, and here v over this is here, and dou t naught by dou t, dou t naught by dou t is there. So okay, so dou by dou r naught, dou by dou t naught, dou r by dou t naught is, as I said, it is dou by dou t naught of vector r dot vector r raised to the power 1/2 minus r dou by dou t, dou by dou t. So it is dou beta by dou t naught and minus beta dou r by dou t naught. So that's the same thing. So we just change here from this previous step. So next step is to plug these values, because dou by, okay, in this equation here this dou beta by dou T naught. Dou beta by dou T naught means you can write 1 by C times dou vector V by dou T naught, and dou vector V by dou T naught is nothing but acceleration. So similarly, dou R by dou T naught, that we have already done, that is minus V. Okay, so here dou by dou T naught of beta is equal to 1 by C times dou by dou T naught of B, and it is nothing but A over C, where A is an acceleration of moving point charge. And similarly, dou by dou T naught of R equal to minus B, and this is means dou V by dou T naught is A. So we plug these things into above equation right there. So here we plug dou V by dou T naught is vector A there, and this is dou beta by dou T naught is 1 by C times vector A, and this dou R by dou T naught as minus B, vector B, minus vector B. So if you do that, we will have a couple of changes here. So it is minus dou A by dou T minus mu naught by mu naught Q by 4 pi. Okay, so dou V by dou T naught was A, so that is A there, and it is nothing but R minus RB. And here minus V over this is R minus R beta square. Okay, that's the same thing as we have there. Is anything changed there? Okay, so this is the things. So we just changes a couple of there inside this square bracket. Okay, so this is so everything is the same as previous equation. So only change is minus R dot A over C plus beta dot V and there. And the next job is to play with this factor, and as we have already done many times, so we may have this is the same thing that we have, and this one is the same thing here, 1 by 2R and 2R vector dou R by dou T naught minus, this is the same thing as previous one. So these 2 and 2 will cancel, and dou R by dou T naught is nothing but minus vector V, so we will plug that here. Okay, and you have mu naught. So okay, look at here, this is dou T naught over dou T, and here dou T naught over dou T. Okay, so you can take this dou T naught over dou T from both the term outside, so you get rid of this dou T naught by dou T inside this square bracket, and you left with A over R minus R dot beta, so right there, minus B over R minus R dot beta whole square, and you left with this in 2 and 2 cancel. You have so this will be dou R by dou T naught will be minus B, that's why there comes minus signs arise there, and you left with this R dot B over scalar R minus R dot okay, so okay, okay, so you have this thing. Okay, that's fine. I think probably we have to evaluate this. So del dot B, beta dot B, okay, you can change this. Beta dot B is nothing but V square by C there. So this is nothing but V square by C. So you left with minus dou A by dou T equal to this minus this thing, dou T naught by dou T, and this whole bunch is, this is from first and this is from the second one. So this is r v minus, okay, minus r dot v over r minus r dot minus r dot a by c. So this is from here, and this one is nothing but v square by c. This is equation 3. It is an expression for minus dou a by dou t in terms of dou t naught by dou t. So next job is to evaluate dou t naught by dou t. Dou t naught by dou t. Okay, guys. So f of t, you know, f of t prime was that we defined. We introduced f of t prime as t minus t prime minus 1 by c times mode of r prime minus r naught, vector r naught at t prime. So similarly, you can have this f of t prime, f of t naught means this is t minus t naught minus 1 by c mode of r prime minus r naught t prime, or you can take t naught, because this is also evaluated at t prime equals to t naught. So if you plug that, and you know that this is your dou f by dou t. Dou f by dou t will be 0. If you okay. Okay, so variation of this factor at t prime equals to t naught. If you take this function f of t prime is your this equals to 0. So that means similarly you can take dou f by dou t naught dou xk, that will also be 0. Okay, so can you obtain the value of dou t naught by dou t with the help of this idea? So if dou f by dou t at t naught equals to 0, then how can you evaluate dou t naught by dou t? Guys, would you like to try this?
By differentiating above equation. So
yes, can you try that? I would like to make sure that how many of you are pretty close, or how many of you can exactly obtain the value of dou t naught by dou t, and how many of you cannot do it at all. So hint is dou by dou t of t f of t naught equals to 0, and f of t naught is t minus t naught minus 1 by c mode of r prime minus r naught t prime or t naught. Try to do that. Plug the value of this. Plug the value of this f of t naught that we have written in previous slide. This one. So many things are there too. Okay, so this is here. F of t naught equal to t minus t naught minus 1 by c r prime minus r naught t naught, t prime or t naught. So if you plug that, so in the very first step, what do you get? In the very first step, you will, when you operate with dou by dou t, you will get dou by dou t of t, that is 1, minus you are going to evaluate dou t by dou t naught by dou t. So next term is your minus t naught. So that means dou t naught by dou t. So you have that minus 1 by c dou by dou t of that mode of something, and dou by dou t can be expressed as actually that something is nothing but your r, right?
R dot B by R.
So what do you get?
R dot B by R.
R dot B by R or beta by R?
Beta.
Beta. No, it's a little bit different. Any? Roll number 13.
हजुर सर
Have you got it?
यसको डिफरेन्सिएसन डो टी नट बाई डो टी को भ्यालु सोध्नु भएको सर.
Yes, dou t naught by dou t, yes. So idea is you have to plug.
1 + b by c आछ क्या सर मेरो?
What's that?
1 + b by c आए जस्तो मान्छ.
1 plus b by c. No. Okay, anybody? Okay, you are given function f t naught, and you are also given the condition that dou by dou t of f of t naught is equals to 0. By using this condition and plugging the value of your function back into there, you need to play with some differentiation, guys. Okay, one step. So this is the thing. One more step. Okay. 1 minus dou t naught by dou t. I think now you can do it. Actually, you know what? These all mathematics, algebra, whatever we are doing, these are very easy.
1.
But unless otherwise you play with that, it looks like very tough and messy. You know what? This factor, this dou by dou t naught whole bonds, this whatever you have here, this is nothing but dou r scalar, dou r by dou t naught, and this is the factor here. This is the factor that we are supposed to evaluate, and that is dou r by dou t naught equals to 0. And we have already evaluated dou capital R scalar by dou t naught or dou t prime many times. Okay, so dou by dou t naught of R scalar equal to dou by dou t naught of vector R dot vector R raised to the power 1/2 is equal to you know that this is 1/2 times 1 over square root of R dot R times dou by dou t naught of vector r square, and that's dou by dou t naught of vector r square is nothing but dou vector r dot dou r by dou t naught, and dou r by dou t naught is nothing but minus v, that we have already gone many times, guys. So it would be better if we would be meeting physically and you guys are working on whiteboard, right? So unfortunately, I cannot insist you guys to work in front of me, and so this is the drawback of online class. Okay, have you got Krishna? Not yet. Okay, so is anybody trying or just waiting for me? Because if someone is trying to just need to wait for him or her.
Sir, maybe 1 by 1 plus r dot beta by r.
1 by
1 plus r dot beta by r.
यही आता सर 1 upon 1 plus r dot beta upon scalar r आता.
Okay, scalar r.
Minus.
Yeah. Okay, check your calculation. Okay.
बीच में minus हो गया सर. 1
okay.
minus.
Check your calculation, please. So this is the things that I was talking about. Okay, so this is 1 minus dou t naught by dou t minus 1 by c dou t naught by dou t and dou r by dou t naught. And this we can play with this dou r by dou t naught. As I said, this is here. It is this dou r by dou t naught can be written as dou by dou t naught of vector r dot vector r whole raised to the power minus 1/2. And that comes out to be this is 1 by 2 square root r dot r. That square root r dot r means your just r scalar. And when you operate that dou by dou t naught with your vector r square, then that will come 2r vector dot dou r by dou t naught equals to 0. And this dou r by dou t naught is nothing but it is minus v that we have already calculated many times. So this 2 and 2 will cancel. And this is minus v. Let's see that what we have. Okay, so this is here. So here we have 1 minus dou t naught by dou t plus 1 by c dou t naught by dou t and vector r dot v over r. You can take this 1 in other side, and you can take dou t naught by dou t as a factor outside, and you left with this calculation here, minus dou t naught by dou t in 1 minus 1 by cr rb, okay, equals to minus 1. So your minus and minus will cancel. And if you, okay, you can take this v over c there, and you can take your LCM there. This will be r minus r dot beta over whole over r. So that will be okay. So when you solve for dou t naught by dou t, so you will get r over r minus r dot beta. So this is here. So do you get pretty close to this?
Yes sir, यही आता सर.
Yes, sir. Yes,
यसमा
sir.
LCM लिएर चाहिँ हामीले अघि भनेको यही हो सर.
Okay, nice. Okay, so now we plug that back into some equation where we have some expression for minus dou a by dou t. So probably that is equation 3, and there we plug this equation. This is everything is the same as equation 3, but the only difference is that in equation 3 there was a factor which was dot t naught by dot t, and we evaluated that dot t naught by dot t right here, and we have it. So maybe a couple of things can be simplified here. So let's see if we can anything do here. So minus dou by dou t equal to mu naught by q, mu naught q by 4 pi. This is r over r minus r dot beta. And so we just take negative sign inside. In equation 3, there was negative sign here, but we took negative sign inside. So sign of this two terms are changed. So first term was plus, and we have now it is minus, and second was second. How come this? Okay, so one of the sign come from b probably. So this is minus b over. Okay, sorry. So we are multiplying this inside. So it is b times rb over r times r minus vector r dot beta whole square, and again we multiply inside. So this is the second term come from this small bracket, and so it is v over this thing times r ra over c. Okay, and this is plus. So b square. This is b square, and this. So this b square by times b over c times r minus vector r dot beta whole square. So this is equation 6. So we derived the expression for minus dou a by dou t. So similarly, we will derive the expression for we will evaluate this minus del phi. So for that, again we take this way. So Liénard Wiechert scalar potential is given by this relation. We know that it is q over 4 pi epsilon naught 1 by r minus r dot beta. Okay, so here so we plug the value of that phi into here. Minus del phi means minus del operated on this phi, and now you can take q over 4 pi epsilon naught as a factor outside, and you can operate inside. So here we are going to operate inside, and okay, so here now you can take this dou I. So dou I means your dou by dou xi. Okay, so because this is your vector quantity, but this gives you the scalar one. That's why I just use one of the some unit vector which indicates the direction of that, because this vector quantity cannot be equal to scalar quantity. So later on this will be when we get the simplified form, then again we will get the vector form in right hand side as well. So here this is dou I means dou xi means dou by dou xi. So this is your r minus r dot beta raised to the power minus 1. So here again the same thing here. What did I change here? Okay, I think this is nothing changed. Qn, this is okay. Okay, this step is repeating here. Now this dou xi means dou by dou xi. So if you operate that on this, it will be minus 1 over times 1 over r minus r dot beta whole square, and we operate on the argument of this bracket. So that is inside, it is this argument is r minus r beta dot. So again when we operate that inside, you will have this minus sign. Okay, this minus and this minus, that comes out to be plus here, and we left with 1 by r minus r dot beta whole square there as a factor. And when we operate that inside, because this dou xi means your dou by dou xi. So when you operate that, it will be dou r by dou xi minus now it would, there are the products, so that will be r dot dou b by dou xi minus beta dot dou r by dou xi. So we'll continue with this. Okay, so here again this comes here. Look at here, dou by dou xi, dou r by dou xi. This can be written as this way. Okay, so so everything is same in outside as a factor. So this, when you operate that, it will be 1 by 2r dot dou r by dou xi. Okay, guys. Okay, minus 1 by c r dot dou v by dou xi minus v over c dot dou r by dou xi. Now what we do is this dou by dou xi of r, that can be written as dou t naught by dou xi times dou by dou t naught. And similarly we do the same thing here, we do the same thing here. That dou by dou xi can be replaced by dou t naught by dou xi times dou by dou t naught. So let's do that. Okay, so everything same as a factor outside. So here this 2 and 2 cancel. Okay. Okay. Okay, one more thing here. This r dot this r. Okay, this r can be taken as ri, and you know this dou by dou xi of r can be taken as this xk minus xok of t. So this is the technique that generally we use in, you know, indices form. Okay, and here, so here we do not change anything here. This is r by c dot dou v by dou t naught times dou t naught by dou xi, and that from here third term we have minus, okay, again dot product of two vectors. This can be written in this form, vi over c dou by dou xi of xk. This r is replaced by, that means v dot dou r by dou xi can be written as your vi times dou by dou xi of xk minus xok of t naught. Okay, and so dou v by dou t naught is nothing but vector a, and if you operate this inside, you will get dou xk over dou xi. Dou xk by dou xi nothing but it is a delta function dou xi. I mean delta ik, and similarly when you operate that dou by dou xi here, you will have dou by dou xi of xok, and that dou by dou xi can be replaced by dou t naught by dou t times dou by dou t naught, and that will give you some results. And similarly here dou by dou xi of xk, that will give you the delta function again, delta ik, and again you will differentiate this one with respect to dou by dou xi, and dou by dou xi can be replaced by dou t naught by dou xi times dou by dou t naught, and that will give you some result this way. Okay, so so ri by r is there. So dou by dou xi we operate inside dou xk by dou xi, which will give you the delta function, and this is dou xok by dou xi and this dou by dou xi can be replaced by that in terms of t naught. Similarly here, dou b by dou t naught is vector a, so r dot a over c dou t naught by dou t naught by xi, and again from this third term it is bi by c is same, and when you operate inside you will have dou xk over dou xi minus dou by dou xi of this bunch. And now this is delta function, and delta function delta ik and delta ik there, and delta ik survive when I equals to k. So wherever there is I, you can replace by k, or it doesn't matter because it survive only when I is equal to k. So look at here, delta ik is there, delta ik is here, and this dou by dou t naught xok, this can be replaced by bok, and similarly dou by xok by dou t naught, that can be expressed as bok. So next step, so it is here it is bok and this is bok, and delta function can be okay. Now look at here, so we removed delta function there just by noting the situation it survived when I equals to k. So so for I equals to k, this comes out to be 1. So if you multiply inside by this quantity ri by r, you have ri by r as a first term, and similarly this ri can be written as rk by r, and bok, this ri by r can be written as rk by r, and this bok is right there, and dou t naught by dou xk minus r dot a, this one is here, r dot a over c dou t naught by dou t, and this bi. So because this our, you can take this when we multiply this inside, so this is I equals to k, so you may have instead of bi you may write bk, but if you write ik bi, that doesn't matter because it is obvious that it survive only when I is equal to k. So this is bk over c, and if you multiply that minus minus plus there, and this is bi and bok, or by c there, and dou t by dou t naught by dou xk. Okay, so next is to evaluate dou t naught by dou xk. Okay guys, again f of t naught is t minus t naught minus 1 by c, this once, and you evaluate this in the condition that dou by dou xk of f of t naught is equals to 0, or you can say this is dou by dou xk of f of t prime evaluated at t equals to t prime equals to t naught, that is equals to 0. By using this function and using this condition, you can evaluate dou t naught by dou xk. Guys, today I would like to stop here, but honestly, do not copy from anywhere and do not catch the things that floating in the air. Just try yourself. Given function is this, and condition is given right there. If you will be able to evaluate dou t naught by dou xk, honestly, okay? So next week, you guys will come with the value of dou t naught by dou xk. First, in the beginning, we will check whether your expression is correct or not. If something wrong with that, then you can just correct yourself, and then we proceed to find dou t naught by dou xk. And when we plug that dou t naught by dou xk in there, then we will be getting minus del phi, and after that we will plug minus del phi as well as minus dou a by dou t back into del phi minus dou a by dou t, and we simplify that, and we separate your acceleration dependent and the acceleration independent part of electric field, and we stick with the acceleration dependent part, which is your radiating electric field due to the moving point charge or accelerating point charge. Okay, so you know what, in the slide when you go step by step it looks like easy, but sometimes if you do not play with this, you do not practice this, it can be, you know, big problem in examination. So you are supposed to do practice all this. Okay.
सर यो सुरुको डेल टी बाई डेल एक्स केलाई के गर्नुपर्छ सर यसलाई मिलाउन?
Okay, wait. You are talking about dou t not by dou t, right?
होइन सर, मैले यही अहिले दिनु भएको छ नि होमवर्क सर, त्यसैमा सुरुमा डेल टी बाई डेल एक्स के हुन्छ अनि त्यसलाई चाहिँ कसरी के हुन्छ त्यसको भ्यालु सर, त्यो त्यसको अलिकति आइडिया दिनुहुन्छ?
Okay, so to evaluate this, let me check where is that green thingy. Basically, you know that this is the function. So what we do is you are taking the derivation of this bunch and keeping that equals to 0. Okay, so dou by dou xk. Okay, this will be your dou t naught by dou xk. Okay.
Yes sir.
And what about this one?
त्यसैको के हुन्छ होला अलिकति भन्दिनु?
Oh, what do you think?
0.
Dou by dou xk of t, that will be 0, right?
Yes, sir.
So this is 0 minus dou t naught by dou xk minus 1 by c dou by dou xk r of r. This is capital R, the scalar quantity, and that equals to 0, and then you play with that, and finally you will get. Okay, so basically we have already done that part. Main part is here. Okay.
Yes sir. Thank you.
Okay guys, see you then next week.
Thank you. Bye bye sir.
Bye bye.
Thank you.